I know some of you are probably going to be able to get this on your own, but let me go ahead and power reduce. Yeah. Half angle, yes, half angle. Okay, I'm recording. Go. All right, so according to last class, this fits the trig sub format because you have a square root. You've got something squared minus something squared. What's our variable here? The variable. X is the variable, A is a constant, right? That's the assumption. So this fits into the very first format, right? The very first format says if we see something like this, we should make the substitution x is equal to a sine theta, right? What's a for us? A, right? Normally that would be like 9, and then we'd say a would be 3 or something like that. But here a is just some number, we don't know what it is. Then we take the derivative on both sides, we get a cosine theta. So that was the second piece of information I said you would have to get. And anyone remember what the third piece was? What the square root thing is. So that whole square root thing, what is it going to turn out to be? Let's see. A squared minus x squared, like that, which is a squared minus whatever we said x was, a sine theta squared. So you square the a and the sine, and you get a squared sine squared theta. Now the purpose of this is that with the correct trig substitution, this square root thing should turn out to be something really nice. And you can see what will happen if you factor out an a squared. Underneath the root, you get 1 minus sine squared theta, which is cosine squared theta. So you have square root of a squared cosine squared theta. Now you have a product, two things being squared. You take the square root of each one, you get just a cosine theta. And that's it. So those are our three pieces, remembering that this simplifies to be this. And when you do that, we should be able to rewrite the whole integral now. So this integral becomes this thing, which was a cosine theta, right? And then don't forget dx. Dx is part of the game too. You don't just change dx to d theta, right? Dx is whatever dx is here. Oh, I forgot my d theta right there. Sorry. When I differentiate, I have to have d theta there. So this should be a cosine theta d theta. Which of those are constants? The a's. So a times a is a squared. Bring that outside the integral. And so we get a squared integral cosine squared theta d theta. And I'm going to ask someone, let's see, Kiki, cosine squared, what formula should we use with this?
The half angle.
The half angle formula. That's what I thought you would say. The half angle formula, or you could also call it the power reducing formula, Kiki.
Nah, I like spider.
Okay. So remember this one, right? Right? This formula on your formula sheet is called the half angle formula. I've been calling it power reducing. I'm just pointing that out because every time I say it, I always say power reducing. So using that, because it's cosine to an even power, we get a squared. Oh, well, you know what? What else should I put out there with a squared? How about that 1/2? This 1/2 right here. Why don't we just take it outside the integral? So 1/2 a squared integral 1 plus cosine, what? To theta in this case, d theta. Make sure my camera didn't move. This thing has a habit of moving around on me. Looking good, looking good. Any questions? Sean, you all right?
Yeah.
Yes?
Wondering with the power reduction on the
Oh, you used the power reducing formula. Yeah. Did you have that memorized?
Yeah, I did it first.
If you haven't memorized, then that's fine with me.
Yeah, you asked for it.
I did. I was curious. But yeah, if you've got it memorized, then that's fine. I'm not a big memorizer. I never have been, so I would never even attempt to memorize that. My brain, as soon as I try and memorize something like that, my brain flushes it the next day. It's gone. So, all right, so here's where we are. We integrate each one of these, right? The antiderivative of 1 is theta, because theta is a variable. And then the antiderivative of cosine is sine, but we have a number in front, so we have to scale by it. So 1/2 sine 2 theta, yes? So we had a 1/2 a squared on the outside. The antiderivative of 1 was theta. The antiderivative of cosine 2 theta is 1/2 sine 2 theta, and then plus c. We've actually done the integration now. So the integration's over. We just need to get everything back in terms of x. So this is where I said come in with a reference triangle. And I recommend you do the reference triangle even if you don't need it. Just do it because it's a good practice. Let's see. Let's start at the tables and go around, okay? So we'll start out here. And what we'll do is when I call on the table, whoever answers, next time I come to that table, you can't answer, all right? So I'll let you volunteer. Help me with the reference triangle. So what information will I use?
Your substitution.
The substitution, which is, in this problem, Zach?
X equals A sine theta.
X is a sine theta. Tell me what to do next.
Divide by A to get your sine theta.
Divide by a on both sides to isolate sine. Draw a reference triangle. Label the angle theta. Opposite over hypotenuse is that ratio. And that always allows you to get this other side, which I'm probably going to need. A squared minus x squared. Good. All right. Next table. Anyone at the next table?
I'll find the theta.
You want to find theta first? Okay, what are you going to go use to do that, Sean?
The x over the a equals sine theta.
You're going to use this to isolate theta? Okay, great. How are you going to do it?
Arc sine.
Arc sine on both sides of the equation. Arc sine of this is just arc sine of that. Arc sine of sine theta is theta. So now I know what theta is, so I'll be able to replace that. Very good, Sean. And then next table. Wait, I said Sean. Sorry, Matthew. Close. You're one table right behind them. Sorry. So anyone on Sean's table, including Sean, I'll let you answer too. We've taken care of theta, which means we have to resolve this. Any ideas of what to do with that? No one else can help. Not yet. Let me help you. Do we know anything about sine of 2 theta? All we have is information about theta, right? And sine of theta. So the 2 theta screws everything up. There you go. So we're just going to use the identity from pre-cal that allows us to take that formula, sine 2 theta, and turn it into 2 sine theta cosine theta. It's called the double angle formula. So I'll rewrite everything. Should I replace the theta now? Is that okay? Sine inverse x over a, and then plus, this is going to become 2 sine theta cosine theta, but the 2 is going to have to be multiplied by 1/2, so the 2 is going to go away. So I'm just going to have sine theta cosine theta. Any questions on where I got that from? All right, back table. Anyone want to tell me what sine theta and cosine theta are? Oh, hold on. What's it? Okay, sine theta is x over a. Good. And then cosine theta? How did you get x over a? You just looked at this right here, right? Which is also coming off of this. If you look at this triangle, sine of this angle is this over this. Cosine is which side over which side? Adjacent over that. right? So you can get those two pieces of information from this triangle right here, right? X over A is your sine. So this is going to become X over A times, and then the cosine. Ruben, you understand?
Yeah.
Okay, this side over this side. So square root x squared minus a squared over a again. Yes?
Did a squared minus x squared?
X, did I write it backwards? Oh, this is correct, right? I wrote it backwards here. Thank you. Kieran's always correcting me. Thank you, Kieran. I'm glad you're catching those things. Because if not, then I have to go back and I have to edit my YouTube video and make a little pop-up thing, right? So I just did that today. Yeah, if y'all ever see something real obvious on any of my videos, like point it out. All right, let me rewrite everything. Let me try and do this all right now in one line. So we have 1/2 a squared arc sine of x over a. That's this, right? And I actually distributed this through, and it's a constant, so I just put it in front. Over here, I have x times this root, right? Over what? A times a, which is a squared, right? That a squared and that a squared are going to cancel out. And so I'm going to have what? Plus 1/2. Right, this cancel with this. X root a squared minus x squared plus c. Chris, I think you're getting old. You're like squinting. I think you're getting old.
I just don't have my glasses.
Oh, okay.
No, he's getting old.
He's getting old.
Where'd that 1/2 come from?
Which one? Right here?
That's one.
This one right here?
Gotcha. You distributed.
Now, look, the way I have it written here, it looks like I did this incorrect. This distributes to this first, right? And gives us the a squared. This distribution to here is where I get the a squareds to cancel, right?
Why don't you just put a squared over 2? Like that works easier.
Why don't I do that?
Yeah.
That's a good question. The reason why I never write it this way, the reason I don't, comes from the fact that in calculus, when we're doing derivatives or antiderivatives, a lot of times, like if you want to take derivative of this, the 2 would come out, right? And so I would want to see the 2 hit the 1/2, I guess. Or if you're integrating, I want that constant peeled away from it so I can integrate this and then put them together. So it's just, I mean, this isn't wrong. It's not more right or wrong, less right or anything. Just that's the convention I use. You're free to do that. Yeah. All right. Now, how many of you have a book that has all the formulas? No one ripped them out of the back yet. Anyone have them? Okay, this is reference page 7, which is not the form. I think your all stops at 6, right, on your sheets? If you look at reference page 7, I told you there's like 100 and something formulas in here, right? This is actually formula number 30. Let me read it and you tell me if it's right. X over 2. Sorry. No, listen, this is the way the formula is written. X over 2 times the square root of a squared minus x squared. X over 2 times the square root of a squared minus x squared. Okay, that's there. Plus a squared over 2 arc sine of x over a. So that is the formula. So these formulas are not actually created some other, weird, mysterious way in a laboratory somewhere, right? I mean, this is just application of trig substitution. They do it generally for a lot of the common things that we see, and they create a table of integrals for you. I'm just trying to share with you that these things don't miraculously appear. Okay, any questions? No? We have more to do. Oh, shoot. Give me just a second here.
need a centimeter.
All right. Okay, if we could, I'm going to show you something. It's completely unrelated to this class, but I ran across it last night. I haven't seen this in a long time. It's going to be about 5 minutes of your life, but I think that there's something in here that's, at least I appreciate. So, have any of you ever heard of Richard Feynman before? What can you say about Richard Feynman? Anyone who knows anything about him? He's a world-renowned physicist. He's one of the greatest minds of recent history when it comes to physics. He just had a unique perspective on things, and so I thought you might appreciate this. Let's see if we can get the volume to work first. I don't know if we're going to hear this or not. Okay, we can't hear it yet, so let me adjust something. Think. Is that the one? Okay. No, I don't hear it. I didn't click it? Oh, I didn't set it. I have to what? I'll set as default for now. What?
You have two things trying to go at once. Like technical details.
All right, I will. Hold on. Oh, whoa, what happened there? I lost my internet? See, I plan on a 5-minute little delay here. It turns into a 30-minute fiasco. There we go.
Just type in 8
There we go. All right. I want to turn up the music a little bit because I think that gives you part of the effect. What happened?
I have a friend who's an artist, and he's sometimes taken a view which I don't agree with very well. He'll hold up a flower and say, look how beautiful it is. And I agree, I think. And he says, you see, as I as an artist can see how beautiful this is. But you as a scientist, take this all apart and it becomes a dull thing. And I think that he's kind of nutty. First of all, the beauty that he sees is available to other people and to me too, I believe, although I may not be quite as refined as aesthetically as he is, that I can appreciate the beauty of the flower. At the same time, I see much more about the flower than he sees. I could imagine the cells in it, the complicated actions inside, which also have a beauty. I mean, it's not just beauty at this dimension of 1 centimeter, there's also beauty at a smaller dimensions. The inner structure, also the processes, the fact that the colors and the flower evolved in order to attract insects to pollinate it is interesting. It means that insects can see the color. It adds a question. Does this aesthetic sense also exist in the law of forms? Why is it aesthetic? All kinds of interesting questions which the science knowledge only adds to the excitement, the mystery, and the awe of a flower. It only adds. I don't understand how it subtracts. If you expected science to give all the answers to the wonderful questions about what we are, where we're going, what the meaning of the universe is, and so on, then I think you could easily become the solutions and then look for some mystic answer to these problems. How a scientist can take a mystic answer, I don't know, because the Holy Spirit still understands. Well, never mind that. I don't understand that. But anyhow, if you think of it, the way I think of what we're doing is we're exploring, we're trying to find out as much as we can about the world. People say to me, are you looking for the ultimate laws of physics? No, I'm not. I'm just looking to find out more about the world. And if it turns out there is a simple ultimate law that explains everything, so be it. That would be very nice to discover. If it turns out it's like an onion with millions of layers and we're just sick and tired of looking at the layers, then that's the way it is. But whatever way it comes out, its nature is there and she's going to come out the way she is. And therefore, when we go to investigate it, we shouldn't pre-decide what it is we're trying to do except to find out more about it. You see, one thing is I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong. I have approximate answers and possible beliefs and different degrees of certainty about different things, but I'm not absolutely sure of anything, and then many things I don't know anything about. But I don't have to know an answer. I don't feel frightened by not knowing things, by being lost in the mysterious universe without having any purpose, which is the way it really is as far as I can tell possible. It doesn't frighten me. And so altogether, I can't believe the special stories that have been made up about our relationship to the universe at large, because they seem to be too simple, too connected, too local, too provincial. The earth, he came to the earth. One of the aspects of God came to the earth, mind you. And look at what's out there. How can it isn't in proportion. Anyway, it's no use arguing. I can't argue. I'm just trying to tell you. With the scientific view, well, my father's view, that we should look to see what's true and what may not be true. Once you start doubting, which I think to me is a very fundamental part of my soul, is to doubt and to ask. When you doubt and ask, it gets a little harder to believe.
All right. Anyway, he was a great physicist. I think he's still alive. I could be wrong there. And my purpose of that is not to try and create a debate. This wasn't supposed to be like a religious thing or anything like that. Just more of just his perspective on the world and questioning and doubting and seeking answers. Just that spirit that I think should be in a lot of people who are in a course like this, where you want to be an engineer. When you're young and in these classes, you still feel this energy that you could actually do something that changes the way things are. I hope that you all have that. I'm a little older, so as you get older, that fire kind of dwindles away a little bit, so I just think that little speech kind of captured, we better. Who knows what YouTube's going to show next? Here. I got it. All right, so let me get back here.
4K, oh yeah, the 4K TVs, oh man. We went to Best Buy the other
What
day.
is that like, 30 minutes just for 50 views of random images?
In 4K, so.
All right, can we get the lights again, Vanessa? Thank you. Where are those notes? There we go. All right, these are the ones from last time. We were finishing up here. And there they were. Okay, that's where we were, right? And we had done the first one, right? That's all I had time for. And I said that we'd come back and do the second one. Right? We did the second one? No, we didn't do one with A, I don't think. Someone check real quick. Make sure I didn't do it. We did not, right? Can we get, Vanessa, one more set of lights? Thank you. All right, so should we do the second one here? What do y'all think? See, because each of these examples has a little bit different result when you do them. So that's why I have these as examples. So let's see if this one gets weird at all. All right, where did we leave off? Back there at Ruben, right? So next table, Justin, Kieran, anyone want to tell me what this actually, this table is going to supply us with all three pieces of information we need for this problem. So whoever wants to go first. Go ahead, Kieran.
X is going to be A secant theta.
X is going to be A secant theta.
The substitution.
Okay, everyone see that off of the formula sheet? Keep going. What do you want me to do now?
Now dx
Okay, dx is,
equals A secant theta tangent
yep, secant theta, tangent theta,
d theta.
d theta. And then the root part, right? X squared minus a squared, which for us turns out to be, now let's switch to someone else at the table.
A secant theta squared.
Okay, a secant theta squared, so is it all right if I write it a squared secant squared theta? That good? And then what?
Minus a squared.
What do you want me to do with that?
Take out a squared.
Take out an a squared, which would leave you with,
Secant squared theta minus 1.
okay, good? Any recollection of what that is?
Tangent.
Tangent squared. So square root a squared, tangent squared, theta. All right?
So it's going to be
A tan theta. Good, good. All right. Moving up to the birthday table. Since it's your birthday, Chris, you want to rewrite that? Tell me how to rewrite that? A tan theta on the bottom, right?
Yes.
Okay, so on the bottom you're going to have A tan theta. That's replacing this. Vanessa, is that good? Yeah, you follow that? Yes? Okay, and then dx. Chris, you keep going?
Yeah.
Okay.
dx would be a secant tangent.
A secant theta, tangent theta, d theta. All right, good. I'll let you go one more step, Chris. What can we do with that?
It looks like you can pull a's out.
Okay,
You can put an a out.
A over A though.
Or they can cancel.
Cancel them out. Anything else?
Cancel out tangent.
Tangent? Good. So which just leaves us with a secant theta d theta, right? So integral secant theta d theta is all that's left. And now we're back here. Who answered here last? Zach was our answer. So Chris, Ivana? Where you? So I think Ivana's on it. She's got the table out. She's got her formula sheet. Because we talked last time that anytime you have a trig function by itself, you're in business. Is it a question or the answer? Okay, hold on. You're next. All right. Do you find the antiderivative? Okay, go ahead.
So it's natural log
Natural log,
secant theta
secant theta
tangent theta
plus tangent theta
plus c.
plus c. What reference page was that on?
That was roughly 6.
Reference page 6. What formula?
14.
14. Formula 14, reference page 6. Reference page 6. All right. Robert, Luke, and Sean. I'm just kidding. So Matthew can't answer, so now you're up. So at this point, once you've integrated with this, you should be thinking of, you need what?
Theta.
Well, do we need theta in this one? We don't have a theta by itself, right? We need secant theta and tangent theta. But what do we always do when we get to this part that I told you to get into the habit of doing? Draw a triangle. Draw a triangle. Okay, so I'm still at this table. What is the information I'm going to use to draw my triangle? What equation do I use?
X equals A secant theta.
X is A secant theta, which was the original substitution, right? That's what you used to construct it. And then keep going.
And then divide by A.
Divide by A. Right triangle time?
Hypotenuse over
Hypotenuse over adjacent. So the hypotenuse, I should label it what?
X.
X, and the adjacent A. Everyone agree?
So,
Yes.
do you assign that angle based on what it equals?
Well, you mean like,
You don't arbitrarily assign that angle, do you?
I'm not sure what you mean by arbitrarily assign it.
That's the angle that's going to be it. Just
It's off of this, I don't know. I'm having trouble. I don't know if you're asking me, like, can you put the angle here?
Yeah.
Yes?
Yeah.
I could put the angle here, but then my triangle would look like, what? This instead. And now opposite and adjacent mean different things because opposite is this one and adjacent is this one.
so is it safer to just put it there?
Whichever way makes you happy.
Okay.
Yeah, this is the way I draw it.
So there's a sense of arbitrary to it.
There is, yes. As long as after you draw it and you look back at this information, this matches your picture. The opposite side, or sorry, in this case, the hypotenuse x over the adjacent side to the angle, that ratio is secant. So that triangle works. Yep. What's that?
It doesn't really matter. Talking myself.
Okay. So what is this side right here?
X squared.
Square x squared minus a squared. All right, good. I think we're ready to continue on, so let's move to the back table there. Who's up, Paul or Deepan or Ethan, right? And you guys, whoever wants, can tell me what this is and what this is, and I'll rewrite it up here. So who wants it? Yep. Okay, so you want me to replace secant theta with x over a? And plus, and then tangent theta you want me to replace with?
Yeah, that would be, wouldn't that be the square root of
Uh-huh.
minus
Yep.
A?
Over a? Am I done? Yeah, I'm done. All right, that's it. What's wrong?
Don't you make it secant x over a plus tangent?
You said one over eight.
No, you're plugging it in.
Isn't what? What?
No, you're right, never mind. You're wrong.
Isn't secant one over cosine?
Secant is the reciprocal of cosine. Cosine is a over x, right? So secant would be x over a. Yeah, which is here also. So that's right. Now, I want to show you something. Because that is correct, and you could box that, and that would be, you'll get full credit on an exam for that. But if you were to do this and look at the book, it would have a slightly different answer, and I want to show you why it would have a slightly different answer. They would realize that you have the same denominator there, right? So you could put those two together like that. And then they would write this. This is natural log x plus root x squared minus a squared. And then minus natural log of what? A, and then plus c, right? But a is a constant, right? And natural log of a is a number, right? Isn't it? Like natural log of a number is just a number. And so if I have some number here and I add a constant to it, do I know what that number is? It's a constant though, right? So what they would do is they would completely dump this from the answer and they would just say plus c. And so you would have this plus c. Right? Just be aware of that. If you're ever trying to check an answer in the back of the book, you're like, what the hell happened, man? That's probably what happened if this denominator just all of a sudden disappeared. If it's a number, that will always happen. Okay, we continue. Last problem here. This is a good one. We haven't done anything like this one yet, which is why it's here. x cubed over 4x squared plus 9 to the 3 halves dx. I've warned you several times about this, so let me bring this up again. That you know what you're supposed to do right now because I'm showing you examples of trig substitution. So you know that this is going to be trig substitution, right? If I erased this x cubed and made it x, it would no longer be trig substitution. This would be basic substitution. Because if I let u be this, right, the whole thing, the derivative of that is just 8x, and I'm off by a constant, and I would do just basic substitution. So we just don't want to lose sight of this, that when you're looking at these integrals, you want to have that, don't have the tunnel vision. You want to be looking at all possible things. Understand? I think you kind of experienced a little bit of that on the test, right? Where you're not quite sure which way to attack certain things. All right, but this one does turn out to be trig substitution. The thing is we have to figure out what this 3 halves power means. So I'll just remind you that back in the day when you were learning about radicals, you were taught something like this, that x raised, the mth root of x meant x to the 1 over m. Anyone remember that, right? And also if you put an n in here, like a power on the x, then all that you do here is you put an n right there. So whenever you have something raised to a fractional power, it really means that you have a power and then a root, right? So this is the same as raising this to what power? Third, and then taking the square root. But it turns out that you can also do it the other way around. In other words, this right here can also be done like this. So it's like an order of operations. This order of operations doesn't matter. This would mean do the power first, then take the root, right? So take x, raise it to a power, then take the root. This version does what? Take x, take the root first, then apply the power. Okay? Over here, what I'm going to do is I'm going to rewrite that expression to the 3 halves in this format. And let's see what we've got. It'll be something cubed. What is it that's being cubed? The square root of 4x squared plus 9? Dx. Does everyone agree with that? All right, so what I'm trying to build to here is to get it to look like what I need for trig substitution. And for trig substitution, do we have something with trig substitution that has a plus between them and these are like squared things? Yes? It's the one that's what? Is it a squared plus x squared on your sheet?
Yeah.
It's a squared plus x squared. But I told you it didn't matter what order that was in, right? Because addition commutes. Commutative property of addition allows you to change the order. So if I have one of these, I can do a trig substitution, right? But I don't have that exactly because of what? The 4. See the 4? The 4 is ruining everything because the 4, this does not say I'm allowed to have anything in front of the x squared except a 1, right? The variable, that has to be a 1 in front. I had some students come into my office today and we worked through a couple of the problems here, these homework problems, and we did run into one of these. And what I told them is that the way that I do it might be a little different than if you go get tutoring on it, or if you have a friend in this class taking it with another instructor, it's slightly different. It's just the way that I do it. And so that's the way I'm going to share with you. Hopefully you follow. It's not like harder, I think. It's just different, all right? So what I do is I try and force this to be a 1. And the only way to force this to be a 1 is to actually pull the 4 out. So I'm about to factor a 4 out. And people will ask me sometimes, like, well, why do you have to be different? Why do you have to do it different than other people? You know, it's just like, why can't you just... And it's not like I'm trying to rebel. It's that later on we're going to do this again with something else. And so it's a skill that you should be aware of. that you can always do something like this. So how about pulling the 4, right? Now, if I distribute that back through, I get 4x squared, but what do I have to put here? 9 over 4, right? 9/4. So that way when it distributes through, you get back 9. But that's the same expression, isn't it?
All of that cubed.
All of this cubed, yes. And dx too, right? All right, so that's where we are. Any questions? Anybody see what I can do with that 4 that I just pulled out? You can separate it, right? You could actually break this into 2 roots, couldn't you? You would have the square root of 4 times the square root of this. So what is the square root of 4? 2? Now be careful, especially those of you who came to my office and we did a problem like this. We have this cubed dx. This right here, square root of 4 became a 2, and then we still have the other part, this, right, underneath the root still.
So you take it out at 16, and 16 is cubed?
I'm going to take,
Oh, never mind.
no, I'm going to take the 2 out, but I've got to cube it first before it comes out. I need you to ask me a question if you're lost on any of this.
So it's going to be a 1/8?
It'll be a 1/8 is going to come out of the integral. No questions from here to here?
Can't you plug in the, what is this one, a squared plus, or x squared plus a squared?
X squared plus a squared. Can't you plug in what?
The a squared plus x squared, the x equals a tan theta.
I can't do x equals a tan theta until the number in front of x squared is a 1, which it is now. I'm saying yes, I could do that now. But I'm realizing this is a constant, and I'm just going to try and just get it out of here.
Okay.
You could do it right here, though. Do your substitution. I just don't like the constant. It kind of bothers me being there. So cube the 2, and then cube the root. And I'll just leave it cubed, like written. You'll see. Let me write it. Cube the 2, you get 8 on the bottom, 1/8 comes out. Integral. X cubed on top still. On the bottom, the only thing left there was that square root x squared plus 9/4, but then that was cubed dx. Are there any questions on that?
Where'd you get the 1/8?
Okay, so on the bottom, I just erased it. On the bottom, I had 2 root x squared plus 9/4, right? And that was all being cubed. Because this is multiplication, when you have like xy to the 3rd power, that's x cubed times y cubed. You can apply the cube to each one if it's multiplication. And so what I did is I cubed the 2, and then I cubed this root. When I cube the 2, I get 8. And then it's on the bottom, so I pull it out as a 1/8. And then I have to cube the root, but I'm not cubing it yet. I'm just leaving it as that. Everyone good? All right, now we can make the substitution. So what is the substitution that I'm going to make?
X equals a tan theta.
X is a tan theta. Now, we do have an a here. It's not the letter a, it's an actual a number. So x is our variable. That means this is a squared, isn't it? If this is a squared, then what's a? 3/2, 3 over 2. It's the square root of that. So x is equal to 3/2 tan theta, using the fact that this was a squared, which implies that a is the square root of 9/4, which is 3/2. Do y'all see that? Where were we? Oh, you have a question? Who has a question?
No, never mind, I saw what
You sure? Okay.
Going a little faster than you did earlier.
I'm going a little fast? I'll slow down. You'll just have to let me know. So there's no questions? You sure? All right. At this point, the 3 things, right? We have one of the 3 things we need. So who's up? Are we back there? Oh, you raising your hand? You want to go? Derivative?
Andrew?
Yep. So this is going to be 3 halves, derivative of tangent is secant squared, theta, d theta, right? The next piece of information is that root thing, right? And this part can be a little bit ugly sometimes. So what is the root part we're looking at? What is it? X squared plus 9/4. So Vanessa, looks like you're volunteering here. X squared for us would be what? Let me erase this. 3 halves tan theta squared, right? So you square the 3 halves and you get your 9/4, right? You square the tangent theta, you get tan squared theta. What's still there though, Vanessa? Plus a 9/4. So what are you going to do? Because there's like a pattern. We keep doing this every time we get to here. So what can I do here? The 9/4, right? They both have a 9/4. That's going to happen every time. That's why we use trig substitution, because this will always have something that factors out, and what's left will simplify. So you're factoring out the 9/4. I'm coming up here. So this is going to be equal to 9/4. And when that 9/4 comes out, let's move on here. Who answered over there? Karen, were you the last one? Or
Yeah.
Should be tan squared theta.
plus 1, which turns into what?
Squared theta.
So factoring out the 9/4, we get tan squared theta plus 1. That turns into secant squared theta. Which turns into 3 halves secant theta. Good. So we're there. Yes, ma'am.
Do you have to show your work for this every time?
This right here? Good question. So you probably know or have seen that.
Or just every time we've done it, it equals?
That's right. That's right. And actually, some books will actually just tell you what it is without actually having to work it out. And some formula sheets that I've seen that I've actually created myself will just tell you what it turns out to be. The reason why I'm having you work through this is because I think it's worth the algebra. It's not terrible algebra, but there's, I don't know. I had a student last semester who took the class, didn't get a high enough grade that they were happy with to move on. They were retaking the class, and so they're not in here right now. But they told me, hey, you're doing this different this time. And I said, yeah, I'm making you actually do it. And he told me that he actually likes this better because now he understands where it's coming from, and it's helping him put it all together, I guess, rather than just kind of some blind thing. But so if you understand that there's a pattern and you want to use it and you've got that in there, good. So if you don't want to show it to me, that's fine. But if you get it wrong,
You're not going to take points
I won't take points off if you don't show that step. Yeah.
Will you add points if we show it?
No, I won't add points either. All right, I'm ready to rewrite the integral, I think. I'm erasing all the information I need. Good job. All right, 1/8. All right, since I erased everything, we're going to go to the think tank. And Chris, you're out. You're the think, officially, that's the think tank.
27/8 tangent.
Okay, so you're doing x cubed right now? You're saying 27/8? What now? Tangent cubed theta. And that's because x originally was 3 halves tan theta. So we cubed the 3 halves and we cubed the tangent. Good. Over, you want to keep going, Kiki?
Over, basically the same thing.
What was that root? The root part? Is that what you're doing right now?
Yeah.
What was that root equal to?
3/2 secant theta.
Secant theta. But then the whole thing's cubed. Is everyone still here? What still needs to be tacked onto this?
The dx.
The dx, which is 3 halves secant squared theta d theta. Okay. Yeah, we're going to get a lot of canceling here, but I just want to make sure everyone sees where everything came from. I erased what I had up here, so I'm trusting the think tank here. Yes?
Is it 3 halves or is it 9/4?
Where?
One of the secant theta.
Where? Here?
No.
Here?
Well, once you cancel everything else, you're gonna.
Didn't we went through the whole thing, and what did we say? I erased it, but what did we say the square root of x squared plus 9/4 was? It was 3 halves secant theta. Right? This came out to be 3 halves secant theta. We haven't cubed it yet, which is going to be the next step. We all good? All right, let me go ahead and cube this. I'm going to cube this down here, and then we'll start canceling things out. And I'll do it up here. I'm trying to stay as high as I can on the board because I know it's hard to see over all this junk around in here. You got what? Cancel what?
3 halves secant squared theta.
No, because so 3 halves.
I've got to cube it first.
Yeah, you have to cancel.
So I have to be a little careful with that. I have 27/8 tangent cubed theta over, now I'm cubing each of these. Cubing 3 halves gives me, hey, 27/8 again. Secant though, cubed theta times 3 halves secant squared theta d theta. See how that changes things? If you accidentally cancel these 3 halves right now, then you're going to have some problems. Well, you'll be off by a constant. That's what will happen. You'll be off by some scalar. See, because these go, right? What about the 3 halves? Take it out. That'll become a what, 3/16 out there? Secants, I can get, what, 2 factors of secant to cancel here, and that'll leave me with how many secants down there? Just 1? So, where are we at? We're back around. So Chris and Zach are good on this table. Ivana, you almost had the last one. What was your name again, sir?
Alejandro.
Alejandro, where's your name thing? I don't know your name. It helps when I see it. Whoa, sorry. What? Can I take this? Did y'all make progress while I was?
I mean, depends on what you're talking about, like our.
Did you get that? Oh. The secant squared here canceled with 2 of the factors of secant. There were 3 secants down here, right? So 2 of them went away. You should have 1 down there.
We do use SubB at the end, right?
I don't know. We're about to find out what we do. What do y'all want? What would you? How do you want to split? What do you mean split the tan cubed? Like? You mean rewrite it all in terms of sine and cosine? That's what I would do. Because if it were secants and tangents together in the numerator, I would start playing with that second method. But because I have a secant in the bottom, I think that's the initial instinct, is to go with sine and cosine. Rewrite everything in terms of sine and cosine. So I'll have sine cubed theta over cosine cubed theta over 1 over cosine theta d theta. And then you flip it, and one of the cosines cancels, doesn't it? When you flip this up, one of the cosines cancels. Which will leave you with 3/16 integral sine cubed over cosine squared. And then